Well, good morning. It is Friday, February the 24th. This is advanced level chemistry here at Spain Park High School. If you are enjoying these exciting videos, please feel free to subscribe to my channel and hit that like button. All right, here we go. Today is a continuation of our discussion of potential energy versus kinetic energy. Temperature is a measure of what? How fast, okay, which is what type of energy? Kinetic energy, and it's a measure of the average kinetic energy. And if you recall, we had the graph. I'm going to go ahead and just put it over here. We had the graph, the Maxwell-Boltzmann temperature distribution graph, that if I have a certain gas at a T1, and then I increase the temperature, what's going to happen to this graph? If I go to a higher temperature, it's going to flatten out and the peak is going to shift to the right. So it's going to look more like this at T2. Because this is the number of molecules. Okay? And this is the speed or the kinetic energy. So what does the area under the curve represent? How much area there is under each curve. The number of molecules. That's what calculus actually is all about. So when you guys get to taking calculus, you get a function, you get a graph of a function. When you take the integral of it, you get the area under the curve. Okay? Now, obviously you don't need to know how to do that, but just the area under the curve. So the area under the blue curve, the area under the purple curve is supposed to be the same. It's just the range spreads out, so therefore the height of the peak. So this isn't the speed, this is just how many molecules. This is the speed. At this temperature, the average number of molecules, the majority, the greatest area under the curve, has that much speed. But at the new higher temperature, the greatest area under the curve is somewhere around here. The speed increased. Temperature measures the average kinetic energy. You heat them up, you speed them up. You increase the number of high-speed molecules, you decrease the number of low-speed molecules. But there's always just an average. Temperature measures the average kinetic energy. So whenever there's a change in temperature, you measure how much heat is required to cause that change by our equation Q equals MCAT, MC delta T, where the mass, specific heat, and the change in temperature. And the specific heat is the value that it says how much energy does it take to cause a specific energy change. Let's get your color periodic tables out that match this one. Your color periodic tables out. If you look on that, you will see that it has the specific heat values on there. So if you just look at some metals, coming down here in this corner, you can see it tells you the specific heat is this bottom left number. That's your specific heat of each element. So I come over here and we look at, okay, let's just look at some fun elements. Okay, we look at, come on, gold, you can see it's 0.128. That means it takes 0.128 joules to raise 1 gram of gold 1 degree. Okay? But what about silver? Silver's 0.235. That means it takes almost twice as much heat to raise 1 gram of silver 1 degree as it does raise 1 gram of gold. Okay? You come over Are there any others? Let's see. So all of them, notice the metals, 0.13, 139, 128, 13, 0.24, okay? None of them are all that high. You can come over here. Aluminum, though, is 0.9. So what does that mean about the amount of energy it takes for aluminum compared to gold and silver? It's higher. So you're putting the same amount of heat in, but you're not getting the same amount of temperature increase. It takes more energy to speed up the aluminum molecules than it does the gold and the silver. Water specific heat is 4.18. So that means it's so many times more greater than these pieces of metal. So that means it takes a whole lot more energy to heat them up, but then that means they have all that energy in them, so it takes that much longer for it to cool down. That's why Hawaii has great weather, because it's surrounded by the Pacific Ocean. It takes a lot of energy to get the temperature of that water raised up, but then over time, it takes a long time for the energy to be dissipated back, and so the temperature of the ocean stays pretty much the same. Therefore, the temperature of the air above the ocean stays pretty much the same. And so you got 70 to 80 degree weather all year long. Okay? Great place to live if you're rich. Okay? So it's very expensive. So we can look at those specific heat values. We use that to determine our phase changes. Our temperature changes. But if we have a phase change, that's a change in potential energy. So right now this water is boiling. But the temperature's not going up, yet I'm still adding heat. Where is the heat going? If it's not making the molecules move faster, if it's not increasing the kinetic energy, if we're not going from T1 to T2, the temperature's remaining constant at 100 degrees, where is that energy going? This is not a rhetorical question, I'm actually asking. Into the air? You see steam, the steam's going into the air. What's the difference between water and steam?
State.
Okay, the state. Reese, what are you saying? Their bonds are broken apart. So in the water molecule, they're all just kind of rolling around. They're going faster and faster as we're heating them up. As I put it in from room temperature, turned the gas on, heating them up, they started moving faster, moving faster, moving faster. But then all of a sudden, they started breaking free. When I start breaking those bonds, now I'm changing their potential energy, because it takes energy to break them. It takes 334 joules per gram to break a gram of water molecules apart from one another. Actually, to break the hydrogen bonds and let them just start rolling around. It takes 2,255 joules per gram to completely break them apart from one another. And if we have ice, we have 6-membered rings. That's 4, 5, 6-membered rings that are going to look like this. Okay, so here's my ice. In order to make it go from ice to liquid, I have to bend and stretch and break those hydrogen bonds. That takes 334 joules per gram to do that, to make it go from the crystal into the liquid where they're just rolling around. Then you continue to heat them up, they speed up, then eventually you're breaking them apart. So, I believe yesterday I gave you this worksheet. Okay, so we're going to go through this worksheet. We need to understand what's going on. At each phase. So this is a standard heating curve for any substance. This one happens to be water. It's going to Melt at 0. It's going to boil at 100. I drew this on the board yesterday for you. Now we just want to kind of really go through this and make sure that we understand all the different parts and what's going on, and then hopefully by the end of today we can start in on calculating some of the math, because I know that's the part that you're really looking forward to. Okay?
If it boils at 100, what does it do at 0.5?
Say that one more time.
Point number 5, what does it do there since it boils at 100?
Okay, well that's a good question. Let's work our way there. I don't want to spoil the fun. Okay? So, if we're down here, if this is water and it's below 0, what state is it going to be in? What phase?
Solid.
It's a solid. It's ice. Okay, so you can fill that in. It's ice. Solid. But this is all in segment 1. If I'm going from negative, each one of these lines is 10, 20, 30, 40, 50. Each line, so this is negative 10 degrees. As I'm in phase 1, section 1 here, and I'm temperature's going up, what is happening to the energy being absorbed? What's it doing? The temperature's increasing, and what type of energy? Kinetic, and what's it doing to the molecules? Speed them up. So you don't think of ice molecules as being sped up, but ice has to warm up before it melts. Ice won't melt until it gets to 0 degrees. Okay? So it's what type of energy did we say? Kinetic energy. So then you go and you look, is there any phase change taking place in section 1? I'll give you a hint. No. Okay, if the temperature is changing, you're changing kinetic energy, you're not changing potential energy. Phase changes always involve potential energy. Phase changes always occur at constant temperature because there are changes in potential energy, which is your latent heat hidden to the thermometer. So, what's happening at point 2? What phase? What phase of, let me see, so what phase are present during segment 2? At this point right here in segment 2, what state is our substance? Not yet.
Still ice.
It's still ice. At the very beginning right here, it's a solid. But what did we say was occurring on this horizontal line? Look at your graph from yesterday. It's melted. So it starts as a solid. What phase is it here? It's a liquid here. Okay? So this is my melting phase taking place right here. So are the molecules speeding up at all? I'm seeing head shaking yes, head shaking no. How would we know if the molecules are speeding up? What measures the speed of the molecule? Temperature. What's happening to the temperature? Staying constant, right? This is the point here. So are the molecules speeding up? Here, the bonds, if we're going this way and melting it, bonds are breaking. And remember, breaking up is always hard to do. Breaking up always requires energy. So breaking up, you're putting energy in. Here, time, you're adding heat constantly to the right. So you're adding heat, you're having to put energy in to break those bonds. Now when the bonds form, when water comes back and bonds form, that's when the sparks fly, that's when the heat's released. And so bonds form, so the same amount of heat, 334 joules per gram to melt the ice, the same 334 joules per gram is going to have to be released to freeze the ice. That's what your freezer does. It takes the heat out. It removes that heat so it can freeze. And again, I think I shared this with you before, but I'll share it again. We're coming into springtime. The peach trees in Clanton will be blooming soon. Okay? And then they're going to bloom, but then sometimes late March, early April, we end up having a late freeze. And the farmers have to go out and they have to spray the tree with water On the night, it's gonna freeze. And I said, that's the most stupid thing you could ever do. Why were you gonna do that? Now they're just gonna freeze for sure. But if they freeze, they spray water on them, and that water has to freeze. It's got to lose 334 joules per gram in order to become ice. Well, where is it gonna lose that energy to? Where does that energy go? When that exothermic reaction, where does the energy go? To the outside, to the surroundings. The system goes down in energy, the surroundings goes up in energy. Well, if I spray the peach bloom with water, it's the surroundings. So when that water begins to freeze, that little bit of energy goes actually into the peach blossom, and then the ice actually acts like an igloo and holds that heat in. And so if you have a mild freeze, it actually protects the bloom because of that 334 joules that's released when the water turns into ice. Now, if it gets super cold, down to 20 degrees Fahrenheit, then you're gonna be, having trouble. But on a light freeze, they can save the crop from dying by using the 334 joules per gram, that latent heat. Okay? So, this is the phase change taking place here. It's melting. So what's the change and what type of energy is being used? Potential. So all of this boiling right here, all of the energy of the boiling water is going into breaking bonds. It's all in potential energy, which will come up and look up there. So let's make sure we're filling in the blanks. I can't, that's too small. Okay? So, what phase or phases are present during segment 2? What did you say?
Solid.
And liquid. They're in equilibrium. You have both. It's ice water. Now, if you have a perfectly insulated cup and you put ice into that perfectly insulated cup, the ice is going to warm up to 0, the water is going to cool down to 0, and then they're both going to be at 0 degrees, and then some of the ice melts, but that causes some of the water to freeze, and they're back and forth. They're in what's called equilibrium. Now, most of the time, we do not have a perfectly insulated cup, and heat from the surroundings is working its way in, and so eventually all the ice melts. But if it was perfectly insulated, that ice and the water would just both be able to coexist at 0 degrees. Okay? What's happening to the energy being absorbed from the heat source? Potential or kinetic?
Kinetic.
What does kinetic measure?
Oh.
Kinetic measures changes in temperature. Is the temperature changing during that phase change? So it's the latent heat, which is potential energy. And then what phase change is taking place? What do we call that phase change? Really high level science. Melting. Okay? Melting. A new term for you. Okay, now you guys can keep looking at this graph as you go here. Okay? So now when we're at segment 3, segment 3 over here, what's happening to the temperature? Is the temperature changing? Yes. So what does that mean? What type of energy is being absorbed? Kinetic energy. Okay? So kinetic energy, now the molecules, now once all the ice is melted, now the water molecules start moving faster and faster and faster and faster. So we're going from 0 up to 100 degrees. Is there any phase change occurring? No, it's just got the water's going faster and faster, and it's absorbing, again, what type of energy? Kinetic. But then we get to section 4. Okay, go ahead and fill in all those blanks. These same questions over and over again. So now we get to 4. What is the temperature changing now? So what type of energy is being absorbed? Potential energy. Okay, so what's happening here? What phase change is occurring? Well, but if bubbles are forming, it's No. Yeah, I'm going here to here. I'm going, this is a liquid. What phases are present? Okay, this is where the liquid starts. This is liquid at the top, but what state is it in here? Gas. So what's my phase change? Well, but rapid evaporation is called boiling. Okay, high level, big terms here. When I get this up to 100 degrees, it begins to boil. And for the 10,000th time, what's in the bubble? Water vapor. Okay? So we got liquid and gas present. Again, they're in equilibrium, just like the ice and the water are here. If we had a perfectly insulated container at 100 degrees, you could have both liquid and gas. Now, once I go above here, now what state is it in all the way up? And here's your answer, Ronnie. So in segment 5, what's the state now? It's all a gas. Okay? So is the temperature changing?
Yes.
Yes. So what type of energy is being absorbed? Kinetic. Are any phase changes happening now when it's in the gaseous phase? No. Now if we got it hot enough, that we could turn it into a plasma, but those don't fit onto our heating curve. Okay, so we're just gonna stick with solid liquid gas. And does anybody remember when you're super cold, almost to absolute zero, what state of matter it says that it forms? Some kind of condensate, I heard over here. Bose-Einstein condensate. But that's only like a millionth of a degree or even colder above absolute zero. So that's not exactly going to be just kind of walking through the streets, you're going to see one. You know? So, but technically it's a state of matter. All right, so we have all of these. So it's real important that you understand solid, liquid, gas, changes in temperatures, changes in kinetic energy. Phase changes is when there's no change in temperature, it's a change in potential energy. We can measure the changes in kinetic energy with Q equals MCAT. Follow me. With Q equals MCAT. We can measure the changes in potential energy with our mass times our heat of fusion, and I'm going to go ahead and be a little bit more specific, heat of fusion and heat of vaporization. Okay? And those values are always given to you. The specific heat value is always given. For water, the specific heat is 4.18. You have the periodic table that would have them on there. Okay? But generally, we're going to be dealing with water. So, let's just look at the last few questions. Okay? So what's the melting point? Based upon the graph, what's the melting point of this substance? 0 degrees Celsius. At what temperature would this sample finish boiling? 100 degrees. Starts boiling and finishes boiling at 100. Starts melting, finishes melting at 0. Now, realize, we're going left to right, all the way, we're going uphill. You're going downhill, the exact reverse is going to happen, except instead of energy going in, energy is coming out. The exact same amount. Law of conservation of energy. Once you break molecules apart, they now have the potential to come back together. You put 334 joules in to break it, 334 joules get released when it comes back together. So when a substance is melting, the temperature of the ice-water mixture remains constant because, don't say an answer out, but pick an answer. Somebody raise their hand and tell me what answer did you pick? What did we say? When the ice-water mixture, when the substance is melting, what type of energy is being absorbed? Potential, which is answer which? C. Heat is, you're adding the heat, but it's being converted to potential energy to break the bonds. When a given quantity of water is heated at a constant rate, the phase change from liquid to gas takes longer than the phase change from a solid to a liquid. In other words, the melting line is only this long, but the boiling line is that long. Pick an answer. Avinash, what you get? You still thinking? Talk it over with your neighbor if you need to. A and B, you have the data right here to be able to determine if one of those is true or false. Okay? Which one is false between A and B? The heat of fusion is greater because we have the two values right here. Obviously, this number is bigger than that number. Okay, so I know B is not the answer. Let's look at C. The average kinetic energy. What measures the average kinetic energy? Temperature. So we could say the temperature of the molecules is greater in steam than in water. Well, what do we know about the temperature during the phase change? During the phase change from liquid to gas, what happens to the temperature? Stays the same. So is this true? The temperature of the molecules is greater in steam. Is the temperature greater in the steam than it is in the water when it's boiling? What do we know about the temperature? Stays constant. So they're going to be the same, right? So that one's not true. Okay? Ice absorbs energy more rapidly than water does. Well, they're both the same thing. They're going to absorb at the same rate. It's the heat of vaporization. It just takes a whole lot more heat. Why does it take so much more heat? What did I say? Why does it take so much more heat? Because it's got to completely break apart. That's exactly right. Melting, you're just stretching and bending. Boiling, you're completely breaking apart. Takes more energy to completely break apart. So let's just be friends, you still hang out, versus I don't ever want to see your face again. The let's be friends generally doesn't ever work out, really. Okay, so that's our phase diagram. So now let's talk about how to calculate energy changes within that. One word. Ooh, that one's a tough one. Let's see. One word. Let me think about it. I'll tell you on the way out of class. All right. So now we look at this. We have all of these values up at the top. Okay? Now, they use slightly different 2264 joules. I gave you 2255. It depends upon who's measuring and what book you're looking at and what temperature. Okay? Now, notice this is kilojoules per mole. Okay, ladies, this is kilojoules per mole versus joules per gram. It all depends upon what unit my given's in. All right? So, given that water has a molar enthalpy of vaporization. What is enthalpy? You ever seen that word before?
Yes.
Okay, that is a fancy foreign language chemistry term. Whenever you see this word enthalpy, you translate it to heat. Enthalpy is heat. It's a heat exchange at a constant pressure. It's a chemistry term, but it's like Spanish. Como está usted? For those of us that don't think it's Spanish, I have to interpret that to how are you? Okay? When I see enthalpy, it's a foreign language to me. I have to interpret it into a language I understand. Heat. Enthalpy equals heat. So whenever you see the word enthalpy, it's heat. We use delta H to represent enthalpy. We don't use an E, we use an H. How many grams of water could be vaporized by 443 kilojoules? Well, I have my enthalpy of vaporization is this, and what are my units on it? What is that a conversion factor between? Say that again. Kilojoules and moles, right? So the question's asking how many grams, which is related to moles, and I'm given kilojoules. So what do you think we would have to do here? What would I start with? 443 kilojoules. Okay, so I have a conversion factor with kilojoules and moles in it, so where would kilojoules want to go? So I'm going to say 1 mole over 40.79 kilojoules. But that's going to give me moles of water. But I want grams. Use the molar mass. And we've all memorized the molar mass of water to be 18.02. So again, moles needs to go on the bottom. So I'm going to say 18.02 grams over 1 mole. I have grams now of water. So that's my answer. I stick the fork in it. So we end up getting 195.7. Do I have somebody agree with that number? 195.7. Okay, but how many sig figs should I have? So 195.7 is really going to be 196. 196 grams of water. So if I put in 443 kilojoules, I can convert 196 grams of water to steam. Okay, now they're assuming that it's already at the boiling point here. So I look at number 2. How much more energy in kilojoules we needed for 33 grams of water to go to steam compared to 33 grams of ice going to water? Well, what 2 values am I going to need to use for that? If I'm going from water to steam, and I'm going from ice to water. Heat of fusion, heat of vaporization, right? So again, my Q, the heat, is going to be the mass times my heat of fusion, my mass times my heat of vaporization. So go ahead and let's see if you can do that. You're comparing the Q for ice, 33 grams, and the Q for water, boiling, at 33 grams. And since you're given grams, which one of these values should you use, the joules per gram or kilojoules per mole? Joules per gram, since you're given grams. But the answer does want kilojoules, but we know how to convert to kilojoules once we get to joules. I guess now would be a good time to take a roll. I know, so you can use that one too, showing 264, and it doesn't, it's always gonna be different. It's the exact temperature they measure it at. Different people measure it. Okay, for the sake of time, we're gonna use these two equations right here. So for steam, the Q of the steam is gonna equal 33 grams times my heat of vaporization, 2264 joules per 1 gram. Now, but it wants kilojoules, so how do I go from joules to kilojoules? How many, is it 1,000 kilojoules in a joule or 1,000 joules in a kilojoule? 1,000 joules, so I'm gonna say, joules is on top, so I'm gonna say 1,000 joules, 1 kilojoule. So joules cancel. What does that turn out to equal? Did somebody just say an answer? No, I just heard a mumble. 74.7. Did two or more agree on that number? 74.7 kilojoules. So that's how much it would take to convert 33 grams of water to steam at its boiling point at 100 degrees. But for water, it's 33 times the 334 joules per 1 gram times 1 kilojoule over 1,000 joules. And that's going to equal 1.2. The reality is, in 33, we really should only have 2 sig figs, shouldn't we? So it really should be 75. And this one to 2 sig figs, what you get on? 11.02, so 11? Are we agreeing on 11? Yeah. So 11 kilojoules here. So it takes 11 kilojoules to melt 33 grams of ice, but it takes 75 kilojoules to boil it. A lot more energy to boil than just to melt. All right, let's do this last one. Does everybody have this copied down?
Do you have to write it out like that? Because I just did the 33 times like the 334 and then divide that by 1,000. It just
Okay, but again, units are your friend here because we need to always know what am I starting with, what's my next step gonna be. So I want you to learn how to use these units because I promise you it will help you to be able to be successful. Okay, so the answer would be yes. I would like for you to write it out this way. Units direct you, especially when we look at this next problem. If you missed it, I'm videoing it, it'll be on Classroom, you'll be able to go back and watch it for your learning enjoyment. Okay, so number 3. It is found that 34 joules of energy are required to melt 7.3 grams of a substance. The molar mass of the substance is 59.8. Calculate the enthalpy, the heat of fusion of the substance in kilojoules per mole. So I want kilojoules per mole. But what am I given? Okay? So this is my question here. So I'm given 34 joules per how much? How much melts? 7.3 grams. So I need joules to kilojoules, and I need grams to moles. Now we can do this as one, or we can do 2 separate problems. Now, are you guys good enough are we good to where we can just say that this is 0.034 kilojoules? Divide by 1,000, move the decimal 3 places. Okay? So I know that that's going to equal 0.0340 kilojoules. Okay? But what about grams to moles? How do I get grams to moles? So I'm going to say 7.3 grams times, it tells me the molar mass, 1 mole over 59.8 grams, and that's equal to two sig figs, anyone? Actually, give me 3 in this case, so we'll carry 1 extra. 0.122. Okay, so now to get my delta H, okay, the nth delta H of fusion, it's equal to 0.0340 kilojoules divided by 0.122 moles is equal to and we're going to do this, the 2 sig figs at the very end here. Now we'll round at the end. And quickly. 0.279, so 0.28 kilojoules per mole. Now we could have done it this way, just real fast. If we were given this in 7.3 grams times 1 kilojoule over 1,000 joules times the molar mass of 59.8 grams over 1 mole. Grams are going to cancel, joules cancel, that's going to leave me kilojoules per mole. I'm going to get the exact same answer. Okay, so if you wanted to do it in one step, you could have done it just like this, where you just set your units up and make them all cancel out. This is the way I would do it, but either one, need 2 steps. If I can change joules to kilojoules. But I know my question is this. This is how I know what I'm looking for. Kilojoules per mole. I gotta take the joules to kilojoules. I gotta take my grams to moles. If you don't know what you're looking for, you'll probably never find it. All right. Good day. It's Friday. Hallelujah. Y'all have a wonderful, restful weekend. Get caught up. What? No homework. We'll just finish this up on Monday and then keep going into the next unit. Okay? All right.